Hello students. Hello students. So in this video we'll be discussing about the crystal field theory and bonding in coordination compounds. Okay, in our last two videos we have discussed about IBC nomenclature of coordination compounds, and we have also discussed about the isomerism in coordination compounds. Okay. So here we'll be discussing first we'll be discussing crystal field theory. Now see, these are the 5d orbitals, the shape of the d orbitals that I have drawn here. So out of this 5 we have 3 planar d orbitals and we have 2 axial d orbitals. Okay, so you see why these are planar and axial. Because in this first 3 orbitals now this this lobes now of the d orbitals, they are present along the planes. Okay, means this is x-axis and y-axis, so it is present in between them. So these are present in the planes, so that's why it is called planar d orbital. So since this is the lobes are present in the xy plane, so it is called dxy. In the second one, the lobes are present in yz plane, so sorry, xz plane, so it is dxz. And the third one, the plane is the lobes are present in the yz plane, so it is called dyz. Okay, and we also have these two d orbitals where the lobes are present along the axis. You see, these lobes are present along the axis, and since these are present along the x-axis and y-axis, so it is called dx square minus y square. And in this one, the lobe is present only along the z-axis. Okay, so it's called dz square. So in this way we have 5 different types of d orbitals. 3 are your planar d orbitals and 2 are your axial d orbitals. Okay, now you see this d orbitals now. Say this d orbitals, we have 5 d orbitals like this. 5 d orbitals we have, and these 5 d orbitals, they are degenerate. Degenerate means equal in energy, means all these 5 d orbitals have same amount of energy. Okay, now what happens in a octahedral complex or any complex, even a means ligands combined with metal to form complexes. In complex, what happens, these 5 d orbitals, they split up. Okay, and after splitting we get a high energy level called Eg and a low energy level called T2G. Okay, so first we'll be discussing about octahedral complexes. Okay, and this splitting up of d orbitals na, it can be explained using crystal field theory. Okay, means in a cubic crystal, how we can, means how the splitting occurs. Okay, means we can explain the splitting of the d orbitals taking the help of a cubic crystal. Okay, so this is our octahedral geometry, this one. So in octahedral geometry, you see we have 6 ligands present at the 6 corners of the octahedron, and the metal is present at the center. Okay, so what we will do, we will just take a cube. Okay, we have just taken a cubic crystal, this one. Just consider a cubic crystal, and you see we'll just consider the metal to be present at the center of the cube. Okay, the metal atom or ion is present at the center of the cube, and we'll consider, means we'll just draw our coordinate system. Say this is x-axis, this is y-axis, and this is z-axis. Okay, we'll just draw our coordinate system, and we'll put the center of the coordinate system, means the origin, we'll put the metal at the origin. Okay, so you see, if we consider this three-dimensional coordinate system, this is x-axis, y-axis, z-axis. Okay, and opposite one will be, this is z dash, this is y dash, and this is x dash. Okay, so these are the 6, means these are the 3 different axes that are present. Okay, now in octahedral complexes, the ligands, they approach the metal from the direction of the axis. Okay, means the ligands, they are placed along the axis. Means you just consider this structure like this, with this, means octahedral geometry. Now with this one, you just compare these two structures. You see this one is, you can just consider this one as x-axis, this one as y-axis, and you consider this one as, say, z-axis. Okay, so these are the 3 different axes that are present. Okay, so let me just erase it. Now see, what happens, since the metal is present along, means just a we consider that the metal is present at the center of the cube, and you see this axis na, this coordinate system, this axis, it is just passing through the face centered. Okay, say the center of this axis, they are just penetrating the center of the face of the cube. Okay, now we see that ligands are approaching the metal towards the axis. Okay, now you just relate this one with the 5d orbitals. Okay, now this 5d orbitals, we have 3 d orbitals which are planar. Okay, and 2 are axial d orbitals. Now you see, if ligands are coming along the axis, what will happen, this axial d orbitals will face more repulsion. This axial d orbitals will be facing more repulsion compared to the planar d orbitals. Okay, is it clear? Because you see, the metal has d orbitals, okay, and ligands are coming along the axis. Okay, so if ligands are coming along the axis, then the metal d orbitals that are along the axis will face more repulsion from the ligand orbitals now. So that's why as a result we get, you see, the x square minus y square and dz square, means the two axial d orbitals, they uh, they experience higher repulsion, so that's why they go to high energy level. Okay, whereas the planar d orbitals does not experience any repulsion, or you can say very little amount of repulsion is being experienced, so they come into low energy level. Okay, that's why you see the lower level na, T2G, it is composed of dxy, dyz and dzx. Means all the planar d orbitals, 3 planar d orbitals are coming in low energy level, and the axial d orbitals are going into high energy level. Okay, so this is the reason why this splitting of d orbital takes place. Okay, and it can be explained on the basis of crystal field theory. Means in the crystal cubic crystal, you can take the example of a cubic crystal, and you can explain this splitting of d orbitals like this. Okay, and this one, whatever we are discussing now, we are discussing it for octahedral complexes. Okay, now you see this thing, this gap na, energy gap between the two d orbitals, the T2G and EG, it is called delta naught. It is called delta naught. It is octahedral splitting parameter. Okay, and this center na, means this line, dotted line, it is called barycenter. Okay, means the energy level of the original d orbitals. Means when you can consider in free metal. Okay, in free metal, whatever the d orbitals are present, that energy level is called your barycenter. And in the complex we get two energy levels, one is your T2G, low energy level, and one is your EG, that is high energy level. Okay, now we can calculate crystal field splitting energy. Okay, this is very very important, because you can also say it is crystal field stabilization energy, because from this one you can easily find out the stability of an octahedral complex or tetrahedral complex. Means any complex, if you calculate CFSE, then you can find out the stability of complexes. Okay, so how you will calculate CFSE? You see, this is the formula for calculating CFSE. Okay, means crystal field stabilization energy is equal to minus 0.4 into x plus 0.6 into y, and whole bracket you will get multiplied by delta naught. Okay, means the splitting parameter. Now see, x and y are nothing but x is number of electrons in T2G and y is number of electrons in EG. Okay, x is number of electrons present in T2G orbital and means T2G level, and y is number of electrons present in the EG level. Okay, so using this formula na, you can calculate crystal field stabilization energy for octahedral complexes. Clear? Now let us move on to tetrahedral complexes. Now see, in tetrahedral complexes, same thing we'll consider, means we'll explain it on the basis of crystal field theory only. So we'll just consider the cubic crystal. Okay, and you see, this is the tetrahedral geometry, this one, and if you relate this one with this cube, you see, we'll just take one corner and the next corner we'll just skip. Okay, means alternate corners we are taking and we are placing 4 ligands. In the cube we have 8 corners, and tetrahedral complexes it has 4 corners. Okay, so we'll skip one corner and we'll place one ligand in the alternate corners. Okay, and the metal same, it will be at the center of the cube. So this one will be your x-axis, this one y, and this one is z. Okay, now see, the ligands, they are not approaching towards the metal along the axis. Okay, means the axis is free from repulsion. So since the axis is free from repulsion, the axial d orbitals, means dx square minus y square and dz square, will face lesser repulsion. Okay, so that's why the dx square minus y square and dz square, they come into low energy level. Okay, whereas you see this ligands na, they are just placed in between two axes, means they are placed along the planes. Okay, so as a result of this, the planar d orbitals dxy, yz and zx, they go into high energy level. Okay, so this is the energy level diagram for your tetrahedral complexes. It is just opposite of octahedral complexes. Okay, now in octahedral complexes we use the term eg and t2g. Okay, but in tetrahedral we do not use the g term. Okay, g is nothing but it is g means g-rayed. Okay, and it is just, it represents symmetry, means octahedral complexes are symmetrical, that's why we use the term g means g-rayed, and tetrahedral complexes are not symmetrical, so we don't use the term g. Okay, so for this one we'll use the term delta t, means crystal field splitting parameter delta t, and the relation between delta t and delta naught is delta t is equal to minus of 4 by 9 into delta naught, and crystal field stabilization energy for tetrahedral complexes is given by this formula. So this formula is just opposite of that one. Previously in octahedral we had minus 0.4x plus 0.6y. In this one it is opposite, it will be minus 0.6x and plus 0.4y. Here x is for eg, also sorry, x is for e, g term is not used here. X is for e and y, it is for t2. Okay, so x is number of electrons in e level and y is number of electrons in t2 energy level. Okay, so this is the reason, means why this d orbitals now, they split in a complex, means in a free atom we have the 5 d orbitals, they are degenerate. Okay, means they have same energy, equal energy, but when a complex is formed, what happens, this d orbitals, they split into two energy levels, t2g and eg, and in tetrahedral complexes it will be t2 and e. Okay, so next this one, let us study this one, ligand field theory. It is also very important. You see, ligand field theory means what? We have different types of ligands. Okay, some are neutral, some are negative ligands, some are positive ligands, like that. Okay, so ligand also have different strengths. Okay, means all ligands, they have different strengths. So on the basis of the strength of the ligand, this splitting of the d orbitals will vary. Say you have this one, say for example say you have this is T2G and EG level. Okay, now if your ligand is a weak ligand, okay, if your ligand is weak ligand, then this gap will be small. Okay, if ligand is weak, say weak field ligand, WFL is called weak field ligand. If it is a weak field ligand, then this gap will be very small. Okay, but if a ligand is very strong, okay, then this energy gap will be high. Okay, so on the basis of this strength of ligands what we've done, we have a series, it is called a spectrochemical series. Okay, and in this series we'll get all the ligands, they are arranged on the basis of their field strength. Okay, so you see this cyanide, CO, carbonyl, then NO2, these are all strong ligands. Okay, these are strong field ligands. Okay, strong field ligands means the gap is very high. Okay, and this ligands, say iodide, bromide, chloride, means all the halogens these are weak field ligands. These are weak field ligands. Okay, So you have to memorize this means this series, because this is very very important, because from this series only you will be knowing that whether we will be getting high spin complex and low spin complexes like this. So what are high spin and low spin? You see we have this configuration D3, means we have 3 electrons in the d orbitals, okay, D3 configuration. And this in the complex we know that say we are discussing about octahedral complexes, okay. So in a complex we know that this d orbitals, they are split into T2G level and EG level, okay. So since they are split into T2G level and EG level, say this one, this is T2G and this one is EG, okay. So T2G level and EG. Now we'll start filling up the electrons from the lowest energy level, okay. And for filling up electrons, the same rules will be followed. Say what are the rules? Pauli's exclusion principle, Horn's rule, and Aufbau principle, okay. So first, since we have 3 electrons, and you see these low energy levels are degenerate, means 3 orbitals are having same energy, so we'll give one electron to each of these orbitals, okay. So in this case we don't have any problem, because we have only 3 orbitals and we'll give them in the lowest energy level, okay. Now let us come to D4 configuration. Say we have 4 electrons in the d orbitals, okay. Then what we will do, you see, say it is just T2G and EG split up. So first we will give one electrons to this orbitals. Now see, the 4th electron, it can either go into the high energy level or it can come back into this T2G level only, okay. So this 4th electron, which orbital it will occupy, it completely depends upon the ligand, okay. Now if the ligand is a strong field ligand, if ligand is a strong field ligand, then this gap is very high, okay. This gap is very very high. So if this gap is very high, the electron will choose to stay in this low energy level, because if this gap is high, it needs more energy for this electron to jump to this high energy level, okay. So that's why the electron will prefer to stay in this low energy level. And if the gap is very small, means we have small gap between the T2G and EG level, then ligand can easily, means the 4th electron can easily go to this higher energy level, okay. So this type of complexes are called high spin complexes, where we feel means where the gap is very small na, so that extra electrons can go to high energy level, okay. So we call this one as high spin complexes. And where the gap is very large, we call it as low spin complexes, okay. So always remember, if you have a weak field ligand, you will have high spin complexes, and if you have a strong field ligand, you will have low spin complexes, okay. Now same thing, let us take the example of D5. We have this one. Say if it is gap is very low, then we will put 1 2 3 in the T2G level and 4 5 on the EG level, okay. And if the gap is high, say we have a strong field ligand, then we'll put 1 2 3 then 4 5 like this, okay. Means we'll get low spin complexes, clear. So next let us move to some examples. Yeah, so now see, on the basis of this ligand field theory and crystal field theory, the splitting of the orbitals and all, so using all these concepts we will be discussing about different types of complexes, okay. So first we will be discussing about octahedral complexes. So octahedral complexes na, these are of 2 types, okay. These octahedral complexes, these are of 2 types. First one is your inner orbital octahedral complex, where the hybridization is D2sp3, okay. And another one is your outer orbital octahedral complex, where the hybridization will be sp3d2, okay. So let us first discuss this one, say inner orbital octahedral complexes for d2sp3 hybridization. So we'll take the example of this compound, okay, this coordination complex FeCN6 4 minus. So in this one, first what you have to do, you have to find the oxidation number of the metal. Cyanide has a charge of -1, okay. So Cn has a charge of -1, so we have 6 Cn ligands, so it is -6. minute. So it will be minus 6. Okay, and we have minus 4 charge outside, so it will be 6 minus 4 is will be plus 2. Okay, so iron is present in plus 2 oxidation state. Okay, now you see the atomic number for iron is 26. Okay, and we have Cn ligand. Cn is a very strong field ligand. So these are the things that are given to us. So first what we'll do, we'll just write the electronic configuration for the metal, means free metal. Okay, means not in the complex, just the free metal. So iron in 0 oxidation state, its atomic number is 26, so configuration will be argon 3d6 4s2. Okay, so what we'll do, we'll just draw these orbitals and we'll just fill up electrons. Okay, we have 6 electrons in the d orbital, so it will be 1 2 3 4 5 6. Okay, and 2 electrons in the s4s orbitals. Okay, now in this next what we will do, we'll just write iron in this complex. So in this complex, iron is present in plus 2 oxidation state, so we have to remove 2 electrons from the free metal. So 2 electrons, we know that it will be removed from the outermost shell, so 4s electrons will be removed and we will get this configuration, 3d6 configuration. Okay, so fill up of electrons will be same, so 1 2 3 4 5 and then 6 1 in the first one. Okay, so 4s and 4p are empty. Now what we have to do, we have to draw this energy level diagram, this one. Okay, because these 5 d orbitals that you are seeing now, is when the complex is formed, these 5 d orbitals are split into this one, T2G and EG. This is your T2G and this is your EG level. Okay, so you see cyanide, this cyanide is a strong field ligand, means this gap is very high. Okay, and I just told you that if the gap is high, the electrons will prefer to stay in the low energy level than going up, because gap is high, so it requires more energy for the electron to go to the upper energy levels, so it prefers to stay in the low energy levels. Okay, so we'll get this one, means all the 6 electrons will be occupying the T2G level. Okay, so now in the complex what happens, you see the filling up of electrons is like this. In the first 3 of the 3d orbitals na, it will be occupied fully and the other 2 will be vacant. Okay, now you see we have 6 cyanide ligands. Okay, means we need 6 empty orbitals for the cyanide ligands to donate electrons, then only coordinate bond will be formed na. So we'll get this 2d, then 1 4s and 3 of the 4p orbitals will participate in hybridization. Okay, so that's why you see the inner d orbitals are taking part. Inner d orbitals means this one, this 2 3d orbitals are taking part in this hybridization, so its hybridization is d2sp3. Okay, its hybridization is d2sp3. Since inner d orbitals are taking place, so it is called inner orbital octahedral complexes. Okay, next you just try this example, FeCN6 3 minus. Same thing, in plus 3 oxidation state we will have 3d5 configuration and we'll just fill up the electrons like this. Okay, then in the energy level diagram you see Cn is a strong field ligand, so gap is very high, so electrons will prefer staying in the low energy level. Okay, so we'll get low spin complexes. So after rearrangement in the complex, it is occupying this one. Okay, now you see same thing, it is also a inner orbital octahedral complexes because hybridization is d2sp3. Okay, so in this way you can find out hybridization of different this one octahedral complexes, and from the hybridization you can understand then whether it will be inner orbital octahedral complex or outer orbital octahedral complex. Okay, we'll discuss outer orbital octahedral complex. One more thing, you see magnetic property. Okay, how we will identify the magnetic property for octahedral complexes. Magnetic property, you see, you just have to check for this one, say in the complex. This is the energy level diagram for the complex. Okay, in the complex you just check, you see this one, all the electrons now in this means all the electrons that are present in the valence shell are paired. Okay, if all the electrons are paired, then the complex is diamagnetic in nature. Okay, and in this one, in the second example, you see you have one unpaired electron, so that's why it is paramagnetic in nature. Okay, Same thing, you'll just you'll be able to know this when you'll just solve it. So I've given you some 3 examples, so you just solve this examples. Okay, this is your homework. So next, let us move on to outer orbital octahedral complexes. So in outer orbital octahedral complexes, what do you have? Say we have this hybridization sp3d2. Okay, means outer d orbitals take part. So just take this one, COF6 3 minus, in this cobalt is in +3 oxidation state. So normal cobalt is 4s2 3d7. So just fill up the electrons like this in this orbitals. Now see, in this one in +3 oxidation state, we have this configuration 3d5 4s0. Okay, so we'll just fill up the electron just like as it is. Okay, in the complex, what happens, this F ligand, it is a weak field ligand. Okay, since this energy level diagram, you just see this fluorine is a weak field ligand, that means this gap is very low. Okay, it means if gap is very small, then we'll get high spin complexes, means electrons will jump up to the high energy levels. So filling up of electrons will be like this: 1 2 3 in the T2G, then 4 5 in the EG, and again 1 left, so it will come in the T2G level. Okay, so we'll get this type of configuration, 6 electrons in the 3d orbitals. Okay, now see, all this 3d orbitals na, they are having at least one electron. Okay, so for hybridization we need empty orbitals. So you see, it will start from this 4s, then 4p and 4d. So these are the 3 orbitals that will be taking part in hybridization. So we'll get the hybridization is sp3d2. Okay, in the previous examples, the 3d orbitals are being used in hybridization. Okay, but in this one, you see, the 4d is used in hybridization. That means the outer d orbitals are used in hybridization. Okay, so that's why it is called outer orbital octahedral complexes. Clear? Then magnetic property, you see here you have this one, unpaired electrons present na? So that's why it is paramagnetic in nature. Okay, same you take this example, NiNH3 whole 6 plus 2, means ammonia is 0, so it will be +2 oxidation state for nickel. So same, we'll get this one, hybridization will be sp3d2, and we'll be getting outer orbital octahedral complexes. Okay, and since unpaired electrons are present, so will be paramagnetic in nature. Okay, one thing you remember, this NH3 na, it is also called as a notorious ligand. Okay, notorious ligand means it sometimes act as a weak field ligand and sometimes it act as a strong field ligand. Okay, now how we will know that when this NH3 will be acting as a strong field and when this one will be acting as a weak field ligand? If NH3 is present in a compound where metal is in +2 oxidation state, then it will be acting as a weak field ligand. Okay, and if NH3 is present in +3 oxidation state, then it will be acting as a strong field ligand. This thing you should remember. Ammonia, if it is present in a +2 oxidation state metal complex, then it will be weak field ligand. If it is present in +3 oxidation state, it will be acting as a strong field ligand. Okay, so you just solve this 4 examples. These are your homework. Okay, next let us move on to tetrahedral complexes. Tetrahedral complexes, all of you know that the hybridization is sp3. So we'll take the example of ZnNH3 whole 4 +2 oxidation state for zinc. So zinc has 3d10 4s2 configuration. Okay, means all the 3d and 4s orbitals are fully filled. Okay, in +2 oxidation state we will have 3d10 configuration, so this d orbitals will be fully filled. So this outer means 4s and 4p orbitals will be taking part in hybridization, so it is sp3. Okay, sp3, and since we have all the electrons paired, so it is diamagnetic in nature. Check this example, NiCO4, this one, where nickel is in 0 oxidation state. Nickel, you see, it has 3d8 4s2 configuration. Okay, so 3d8 4s2 configuration, it is like this. Okay, and since metal is in 0 oxidation state, so means we don't have to write for oxidation state. Okay, So you see what happens there, carbonyl na CO, it is a strong field ligand, this one. So if it is a strong field ligand, what will happen, you see in 3D we have 8 electrons, and 4s we have 2 electrons. Okay, so what it will do, it will push this 4s electrons to the 3D orbitals. Okay, because the ligand is very strong, so this 3D electron means 4s electrons will be pushed into the 3D orbitals. Okay, so after rearrangement you will get 3D10 4s0 configuration. So this sp3 means 4s and 4D orbitals will be taking part in hybridization. Okay, so its hybridization is sp3. And you see all these d orbitals are fully filled, so no unpaired electrons, so it is diamagnetic in nature. Okay, so the last of this types of complexes are square planar complexes. Okay, so in square planar complexes we have dsp2 hybridization. Okay, in tetrahedral we had sp3 hybridization, and in square planar we'll have dsp2 hybridization. Okay, so we'll take the example of NiCN4. Cn is a strong field ligand. Nickel has this one 3d8 4s2 configuration, and in this complex nickel is in +2 oxidation state. Okay, so +2 oxidation state means what we'll do, we'll remove this 4s electrons, so we'll get 3d8 configuration. Okay, now since this is a strong field ligand, it will push this one electron to come inside. Okay, and it will be paired, so after rearrangement we will get this type of configuration. Okay, now in hybridization this 3d orbital will take part, this 4s will take part, and 2 of the 4p will be taking part, so that's why this hybridization is dsp2. Okay, and if you get dsp2 hybridization, then it is a square planar complex. Okay, and since all the electrons are paired, so it is diamagnetic in nature. Clear? So one last thing in this topic, say we have this one, color of coordination compounds. Say we all know that this one inorganic compounds are very colorful. It's all the inorganic salts that you'll be getting, say copper sulfate pentahydrate or zinc sulfate. Say copper sulfate pentahydrate is blue in color, and zinc sulfate is green in color. Okay, so that color of this means coordinate complexes means inorganic salts, the color from where it comes. Okay, so see this color of compounds they occur because of this dd transitions, means dd electronic transitions. Okay, just now we have discussed the d orbitals in a complex, they split into T2G level and EG level. Okay, means low energy level and high energy level, means 2 energy levels are there. Okay, now you see this, if we have empty orbitals in the EG level, means upper energy level, if the orbitals are empty, then if we provide some amount of energy, then this electrons that are present in the low energy level can jump up to this high energy level. Okay, so you see this electronic transition will occur for some amount of energy. Okay, and we know that energy is equals to h nu, means some frequency is associated with a particular amount of energy. Okay, now if that frequency it falls into the visible region, then we'll see some colors. Okay, so that is the reason why we see color of coordinate complexes. Okay, now this concept of color can be well explained using the color wheel. This is the color wheel, and in this color wheel we have 6 colors: V, B, G, Y, O, R, means Vibgyor. Okay, V, B, G, Y, O, R means the color that you see in the rainbow. Okay, now just take this example. Say we have supplied white light, means light that is coming from the sun, h nu, through a solvent. Okay, now the solvent, it absorbs red color. Okay, and it absorbs red color from the white light, and the means in this one, the light that is emitted, so this is the incident light, it is white light, means directly coming from the sun, it falls in this solvent, it's absorbs the red color from the white light and it emits the other part. Okay, now according to color wheel, what we'll see, you see, I means this one, red color, the opposite color for red is green. Okay, means this concept of color wheel, it tells us that if any compound or any, say any substance or any solvent, if it absorbs any color, okay, so in this case red color is absorbed, then the light that is coming out, okay, means the light that is emitted will show this one, the complementary color. Okay, means in this solution red color is being absorbed from the white light, so the light that is coming out of this solution will see it as green colored. Okay, say if this solution would have means absorbed violet light, then we would have seen yellow color, and if this would have been absorbed blue light, we would have seen orange color. Okay, or orange light is being absorbed, then blue color will be seen, means the complementary color is being observed. Okay, so I think with this we will end up with this video. So thank you. If you have any doubts, you just post it in the group. Okay, thank you.